Well, let me talk about scalar measures of model fit. And here's a summary. For a scalar measure of model fit, okay? For scalar measure, we only have a single number to summarize the overall fit of a model. And it is quite useful, right? Very compact, very condensed, right? One number to summarize the model fit. Such a measure might aid in comparing competing models. Within a substantive area, measures of fit provide a rough index of whether a model is adequate. So roughly. For example, if prior models of labor force participation routinely have values of 0.4 for a given measure of fit, you would expect the new analysis with a different sample or with revised measures of the variables would result in a similar value for that measure of fit. The desirability of a scalar measure of fit is clear, but their use sometimes can be problematic, especially for pseudo R-squares later I'm going to talk about. So for example, Allison on his website, Statistical Horizon, stated in 2013, unfortunately, there are many different ways to calculate an R-square for logistic regression and no consensus on which one is best. Long, 1997, I'm aware of convincing evidence that selecting a model that maximizes the value of a given measure of fit results in a model that is optimal in any sense other than the model having a larger value of that measure. Okay, so the message here is probably we can just use a single measure, scalar measure, to select and compare models. Probably have to turn to multiple ones. Okay. So here, I want to talk about three major types of scalar measures of model fit. First is pseudo R-squares, or coefficient of determination, right, in linear regression models. Okay. Usually, such measures are bound between 0 and 1. And Seth in 1985 proposed basically 8 properties for a good R-square statistic in linear regression models. And these 8 properties supposedly or putatively hold for the R-squares in nonlinear categorical and limited response variable models. Okay, so here I just mentioned one, usually bound between 0 and 1. There are a total of 8 properties. I'm not getting into details. Okay. And also, second major type is information theory-based measures, including AIC and BIC. Usually, for such measures, there are no boundaries, and the smaller the value is, the better the model fit is. Unlike R-square, usually the higher the value of R-square is, the better the model fit. And the last type is what I call goodness of fit test. So this is a test, a statistical test. And I'm gonna talk about only one measure, that is Hosmer-Lemeshow test, roughly the pronunciation of that. So first is Bayesian information criteria. So I'm gonna begin with information theory-based measures. So first is BIC, that is Bayesian information criterion. And this criterion is based on the log likelihood. Okay, so the BIC, what we call BIC for model K, right? So it is -2 multiplied by log likelihood, okay? And minus degree of freedom, okay? Multiply by taking a log of the sample size, N. And here, the log L, parentheses, MK is the log likelihood from ML estimation. And the degree of freedom is basically total number of cases minus number of parameters in this model. Okay? And so it's basically number of observations exceeding number of parameters. There is another BIC, it's called BIC prime. BIC prime basically uses an LR test. And it is equal to, BIC prime is equal to negative G squared plus degree of freedom multiplied log of N. Same thing, the second part. The first thing is basically using a statistic from a G square. And the G square is the LR test that all slopes are 0. So here it's comparing two models. One is, the unconstrained model with all the slopes, right? And another model is the intercept only model. And that is the statistic here. And negative 1 multiply that statistic, then that to the second one. And the results, okay, should be, the numbers here, BIC prime and BIC they got to be different. But when we use these numbers, okay, different numbers, okay, when we compare models, the smaller BIC, either BIC or BIC prime. Of course, when we use BIC, we got to use BIC, right? We're not supposed to use BIC prime, compare the number with BIC. And we're not supposed to use BIC, compare with a BIC prime. So when we use BIC prime, got to be BIC prime. When we use BIC, got to be BIC. When we compare these numbers, the smaller one has better fit. So either using BIC or BIC prime should lead you to the same conclusion. And Raftery, okay, agent Raftery shows that 2 times the log of, the probability of observing data given a model 2 over the probability of, observing data given model 1, okay, is equal to BIC 1 minus BIC 2. Okay, so BIC from model 1. And this is BIC from model 2. Okay, and BIC 1 minus BIC 2 is equal to equivalent of BIC 1 prime minus BIC 2 prime. Okay, accordingly, we're going to choose model 2 if BIC 1 minus BIC 2 greater than 0, which leads to BIC 1 greater than BIC 2. Well, just in simple words, the model that has smaller BIC, either BIC or BIC prime, is a better fitting model. Okay? Okay? The smaller BIC or BIC prime is, the better the model fit. Okay? And people say, well, how small it is? Well, here is a rule of thumb. If the difference is 0 to 2, there's a weak evidence. From 2 to 6, that's positive. And 6 to 10, that's strong. And greater than 10, very strong evidence of favoring the model with smaller BIC. But again, there is no scale boundary here. Let's say for R squared, we know it's from 0 to 1. Okay, so for BIC, it's basically it's unbound. And these are kind of relatively speaking subjective. And next, I'm going to talk about Akaki's information criterion. Akaki's information criterion. Now, of course, it's published by Akaki, a Japanese statistician, and wrote a paper in, I believe, in IEEE, and that paper turned out to be one of the most cited papers of all scientific disciplines. So AIC or AIC information, Akaki information criterion equal to -2 multiply log likelihood plus 2k. And log likelihood, this one is the likelihood of the model. And k is the number of parameters in the model. Okay? K is the number of parameters in the model. Okay? Again, same thing for Akaki information criteria. The smaller the AIC, okay, the better the model fit. Now